I'm going to be talking about how we can use MATLAB and Simulink in order to simulate a system which performs power spectral estimation. And so what the idea of this is that if we have a real signal, an ideal signal, which has some noise superimposed upon it, which is typically what we see in the real world, right? We usually don't have just an ideal signal, but there's usually noise. If we want to figure out which frequency bands contain our signal's energy, or which frequencies our ideal signal is located within, we can perform something called non-coherent integration. And this allows us to sort of see our ideal signal's spectral content while sort of reducing the noise's spectral content relative to our signal. And so we're going to set up a system which has a sampling rate of 1 kilohertz. We're going to generate a sinusoid which has 100 hertz frequency and an amplitude of 1 volt. And then we're going to generate Gaussian noise, random noise, with standard deviation of 5 volts. Now, for our simulation, we're going to use frame-based simulation, and this is different than sample-based simulation. So a lot of real systems, instead of just taking in one sample at a time and then performing some computation, they'll collect a frame of samples, so a collection of samples, and once those are collected in some buffer, those will be passed to the rest of the system for some computation or some signal processing algorithm. And so in our simulation, we're going to use 50 frames, and we're going to use 256 samples per frame. Now we're going to define another variable, nFFT, which is just going to be the number of points we're computing for our FFTs that we're going to use. We'll make that equal to the number of samples per frame. So every time we collect a frame of data, we're going to perform an FFT on those points and do some other operations. And then we can compute the total number of samples that we want to simulate is going to be the number of frames times the number of samples per frame. And the simulation time, since we're starting at a time of 0, we're going to use the number of total samples minus 1, and that's going to be divided by the sampling frequency. Lastly, we're going to define this an average variable, and this is going to be the number of power spectra that we are averaging together in our non-coherent integration. So you can see here the Simulink model that we're going to use, and it's in red because I haven't actually run it yet, so it's using parameters that haven't been set. But I'm going to show you the layout and what's going on here, and then I'll show you all the parameters that are used in each of these blocks. So we can see here that we have a discrete sinusoid signal, and that is going to be sent out to our workspace. And so this is using the sine wave block from the DSP system toolbox. And this workspace block can be found in Simulink sources, I believe. Let's see, to workspace in Simulink syncs folder. And so we're going to send this signal out to our workspace. In addition, we're going to connect this signal up to this periodogram block. What this periodogram does is it takes some number of averages of the power spectrum of a signal. So we're going to generate some number of frames, I believe we chose 50 frames, of this sinusoid data, and this periodogram is going to take 8 consecutive frames and average their power content, and it's going to take a running average, or a moving average. And now we're going to pass this data, which contains our power spectrum, to this selector block, which we'll have configured to take only the positive half of the frequency content here, since we have a symmetrical power spectrum for a real signal. So only the positive frequencies are passed along, and those are going to go out to our workspace. The next thing that we're doing is generating random noise, and so we use this random source block, which can be found in, again, the DSP system toolbox under sources. And so we generate this noise and we add it to the sine wave that we've generated using this sum block. And you can find that just typing sum, and it's in Simulink math operations. Once we sum those together, we're going to break those out to a spectrum analyzer, so we can see that we have the signal with the sine wave plus noise going to the spectrum analyzer, and we also have just the pure sine wave going to the spectrum analyzer, so we can compare the two. And this spectrum analyzer block can be found also in the DSP system toolbox under sinks. So now we see that the random signal plus the sine wave are going to go along two separate paths. One path is an exact replica of what we see down here. So we're going to send it through a periodogram where we're going to average eight collections or 8 frames of power spectrum data. And then we're going to take just the positive frequencies content, and we're going to bring that out to our workspace. Along the other line, we're going to take just a single FFT, and we're going to again select only the positive frequency components and output that to our workspace. So we're going to be able to see the difference between averaging 8 power spectra, and then we'll take this FFT, compute the power spectrum for just a single frame, and see the comparison between the two. So for our random noise, we're going to be using Gaussian noise. We're going to give the noise a mean of 0 volts, a variance of sigma n, and actually we need to square this since we're talking about variance and not standard deviation. And then we're going to provide sample time of 1 over the sampling frequency and number of samples per frame. Here we can see the parameters for our sine wave, and so we have an amplitude of A that we're using, a frequency of f1, phase offset of 0 radians, and then a sample time of 1 over the sampling frequency, and lastly the number of samples per frame. So we can see here now the parameters for the periodogram block, and so we're going to take the mean square spectrum measurement, which is just going to get the magnitude of data, square it to get the power spectrum, and we're going to use a Kaiser window before we find this FFT. And so we use the Kaiser window with a beta value of 5, and we're going to have an FFT length and a number of spectral averages that we defined in the MATLAB script earlier. And so again, this block is going to take an average, which we defined as 8 power spectral averages, or 8 consecutive frames power data is averaged. So here we can see the selector block, and we're going to choose for the index option a starting index dialog. And so we say we're going to start at index 1, and we're going to have an output size of n FFT over 2. So what this is going to do is this is going to take the n FFT points coming out of either the FFT block or the periodogram block, and it's going to take from the first index corresponding to the DC frequency content, and it's going to take n FFT over 2, or half of the frequency content, and that's what it's going to pass along. So it's basically going to cut out all of the negative frequency content. One thing that I forgot to mention is that we can set our stop time up here with this sim time that we defined in the MATLAB workspace, and we computed that based on the number of frames that we wanted multiplied by the number of samples per frame divided by our sampling frequency. And in addition to that, you can see these little dimensions. If I zoom in here, we have dimensions along with each of these blocks, and the way that you can find that for yourself, it's actually very useful because it shows us the number of elements that are being sent from one block to another, and so it helps us to interface and to set certain parameters so that we know how many data points to expect for each block. You can see that by going to the Debug tab, then choosing Information Overlays, and then choosing the Signal Dimensions tab or button. Note that we're able to name the names of the signals that we're outputting to the workspace. So you can just simply click on the block and then click on it again to edit the name. So you can see I've named this block ideal. So the signal output by this will be output in the object out, and that object out has a member ideal. And also I've named this other one actual, so you'll see out.actual. And all the other signals that are being output to the workspace will have their corresponding names, and so that's how you can access the data after the simulation in the MATLAB workspace. So after hitting the run button, the spectrum analyzer is going to pop up, and we can see two signals here. First of all, along the x-axis, I'm only plotting the positive frequencies, and the way that you can do that is by clicking on View, then hitting Spectrum Settings, and this little sidebar pops up. Here I've selected f-start, so you can supply a starting frequency, which I'm going to choose 0 Hz, and then a stop frequency, which I'm choosing 500 Hz, which is our sample rate divided by 2. So we look at the positive spectrum, and we see first this yellow signal is the ideal signal. So for our ideal sinusoid with no noise induced, we can see a pretty distinct peak here, and not really any content outside of that main frequency band. But for the blue signal, where we have noise imposed, we can see that we do have fairly high amount of noise. And although the peak of our main signal does stand out still at this noise level, it is harder to pick out clearly than with the yellow signal. So now back in the MATLAB script, you can see this line right here allows us to simulate our Simulink model. So you just use the sim command and you give the Simulink model name, and it'll simulate it, and it'll output this out object. And you can see the out object has properties actual, ideal, and all the other names of the signals that I've output to the workspace, in addition to this T-out vector, which is going to be the times at which the frames we use were produced. And so we can see here, I'm going to change this to 30 for a second. I'm going to show you the difference between a single power spectrum, a single frame, versus the averaged periodogram, or the non-coherently integrated power spectrum. And so we're going to use an arbitrary frame of 30, to show this, and I'll tell you about why this warning is here in a second. So first what we're going to do is we're going to define the positive frequency axis, which is going to go from 0 Hertz, or really 0 radians per sample, and but in this case I'm going to plot in Hertz, so from 0 Hertz up to the sampling frequency over 2 minus 1 frequency resolution. And we're going to have n FFT points over 2, since we're only looking at the positive half of the spectrum. And so here you can see that I'm extracting the FFT data. This is going to be that single FFT data, and it's stored in the out object, in the spectrum member, and in the data member of that. Now you can see that data is complex double, so it has complex Fourier transform coefficients. And what we see is that it's 128 by 1 by 50. And so what this means, the 50 is the number of frames that we've simulated, and the 128 is going to be half of the number of samples per frame. So we defined 256 samples per frame, but when we used the selector blocks, we actually selected only the positive frequencies, and so we only took half of the coefficients. So that's why we see this 128. So if we take the spectrum data of the signal with the sine wave plus the noise for the 30th frame, we're going to get that data, and we're going to plot the absolute value squared, so the power spectrum, multiplied by 2. Since we're only looking at the positive frequency components, we have to multiply by 2 to get the true power. And then we can see I'm going to extract the power spectrum data, the averaged periodogram, at the same frame, and again multiply this by 2. So this is going to be the power data of the sine wave plus the noise, averaged over 8 frames, the 30th frame being the last frame, and then multiplied by 2, since we're only looking at the powers, or the power spectrum of the positive frequencies. And lastly, we're going to look at the ideal periodogram, which is again averaged over 8 frames, and that's going to be the periodogram of just that ideal sine wave. So here we can see the plotted results of the outputs of the periodograms and the FFT data. And so what we can see from this, first let's look at the ideal periodogram, so the third signal, the green one. And we can see a green peak that goes right up about until 0.4, maybe 0.42. And it has a strong peak, and everything outside of that peak is basically 0. and that's because this is showing our ideal signal, our ideal sinusoid with no noise. And so we have no noise in other frequency bands. All we have is content around 100 hertz. And so we see that this changes when we look at the single FFT of our sinusoid with noise imposed. We get this blue signal. So we still have a blue peak that goes right up about until 0.42, but we see these spikes that are outside of the frequency content of our ideal signal, and we see that they go relatively high. And so this noise, if we had a higher noise level, this could really make it difficult to find where our actual signal content is located when these spikes get comparably large compared to the main peak. And so in order to reduce these spikes, what we can do is we can take the averaged periodogram, which is what this red peak is going to show, this red signal. And so we see that the peak is approximately where the other two peaks are, but we can see that the noise content, two things have changed about it. One, the bias, or the average value of the noise, has increased a little bit, but the variance of this noise has decreased, and so we don't see as many of these sharp spikes as we do in the blue data. And so basically what this non-coherent integration, or this power spectrum averaging, does is it increases the bias of the noise, but it decreases the noise variance, which makes it less likely for us to have large peaks that look like they could be, signal content. So we can see here the results for frame 2, and the reason that I had a warning in my code whenever the frame number selected is less than the number of averages is because of how the periodogram block operates. So we can see that the single FFT frame, which is only taking data from frame 2, remains similar to before. We actually have slightly higher noise peaks and a slightly lower signal peak. But we can see that the power data from the periodogram is very low. And the reason for that is because we're taking 8 averages, the block assumes that we have 8 frames of all zeros beginning. And as we collect each frame, we get more and more data. So starting with all zeros, then we collect 1 frame. We now have 7 frames of zeros and 1 frame of actual data. And we average all those together, and so we'd expect to see about 1/8 the amplitude of our expected power spectrum. And so here we're looking at frame 2, and so we would expect to have 2 frames of good data and 6 frames of zeros, and so this is why our amplitude is approximately 1/4 of what you would expect it to be at our peak. And once you get to frame 8, which is the number of averages we're taking, then you'll expect to see an amplitude consistent with that of the single frame FFT. So now we can look at the signals, what they actually look like for a given frame. And so I'm going to choose frame 8, and we're going to see how the signal with noise compares to the signal without any noise. And you're going to see, to the eye, it's very hard to see that you actually have a clean sinusoid signal. But when we actually use the non-coherent integrating technique, we're able to bring out in the frequency domain that we actually do have basically one single peak. So here we can see the actual plot of our signals, our signal with noise, and then our ideal signal as a function of the sampling index. And so the signal with noise, you can see maybe some sinusoidal behavior, but a lot of it looks just like random noise. It's hard to see any oscillation, but in our ideal signal, clearly we have a sinusoid. And looking at the different amplitudes, the sinusoid is going from 1 to -1, peak to peak. And the signal with noise, we can see sometimes reaches up to 6 volts or -6 volts. And so it's kind of amazing to think that we can actually get a decent power spectral estimation for this data, but it is possible, especially with non-coherent integration. So the last thing that I want to show is results for very large noise, and so I've actually changed the noise standard deviation to be equal to, 10 volts. So the standard deviation of the noise is 10 volts, and we can see here in the spectra that for the single FFT, our signal, which is at 100 hertz, has a peak, but it's comparable to this peak at 40 hertz, and it's much less than this peak at 171 hertz, and this peak over here above 400 is much more prominent, and so we can't tell where our ideal signal actually is. But when we perform power averaging or non-coherent integration with this red signal, we see that we do have our peak around 100 hertz, and that the noise, although the variance of the noise, or the expected value of the noise, or the average, has increased, it does remain relatively flat along all frequency bands, and so the variance of the noise has decreased, and we don't see these large peaks. So we are able to make out our actual signal's power information.